This video is going to be a relative motion example. Let's say that you are out on a lake in a kayak. There's a dock, so you are here. There's a dock directly east of you, and that is 400 meters away. You know that you can paddle at 1.5 meters per second in still water. And you also know that there's a current that's pointed 30 degrees north of east of 2 meters per second. So there is a current this way, hopefully that's exaggerated, 2 meters per second at 30 degrees north of east. I would like to know, 1, how should you orient your kayak to make it to the dock? And 2, how long is it going to take you to get there? First question. We are looking for how should you orient. How should you orient means we are looking for some kind of an angle. And then the second one, how long will it take? We'll get back to that, but that's going to be a time. So what we're going to do is say, we know our velocity in still water. We are going to take our boat, our kayak, and we are going to have to steer kind of this way and point ourselves in some direction over here. When we do that, the water current is going to carry us back upward, and even though we will be facing kind of diagonal toward the south, we are going to end up traveling on a path that goes directly there. So we are trying to find an angle here. This is a relative motion question, and it's helpful to be able to get some kind of labels on this. So this thing right here, this is the velocity of the water relative to the dock. And this one is the velocity of the kayak relative to the water. So we are going to say the velocity of the kayak relative to the dock, because that's what we want, the dock isn't going anywhere, is going to be the velocity of the kayak relative to the water plus the velocity of the water relative to the dock. Just like before, water and water kind of cancel, and we are left with kayak relative to the dock, and that's what we want. So we need to do some vector addition. I'm going to take this velocity of the water relative to the kayak and break it into components. I have an x component and a y component. Here is the velocity of the water relative to the dock, and this is the y component. This one is the velocity of the water relative to the dock, and that's the x component. So for the x component, I'm going to end up with the cosine of 30, and this comes out to be 1.73 meters per second. For this one, I'm going to end up with a sine of 30, so 2 meters per second. Sine of 30 degrees, and that's 1 meter per second. Now I've got to figure out what to do with this other thing, this velocity of the water, or of the kayak relative to the water. And I'll do that next. The velocity of the kayak relative to the water, I'm going to, again, break into 2 components. Here is the x component. Here is the y component. So this is velocity of the kayak relative to the water in y. This one is the velocity of the kayak relative to the water in x. The kayak relative to the water in y is going to be a negative 1.5 meters per second times the sine of phi. 1.5 meters per second because I know what my velocity in still water would be. And this one is going to be a positive 1.5 meters per second cosine phi. Now I'm about ready to make a table. I'm doing some vector addition, and tables are how I generally do that one. So this is the equation that I am trying to work. I'm going to put those as my rows. Velocity of the kayak relative to the water, velocity of the water relative to the dock, and then velocity of the kayak relative to the dock is the sum of those. And I can put in as much of this as I'm able. First, the velocity of the water relative to the dock. I've got both of those. This is a 1.73 meters per second. This is a 1 meter per second. Now the velocity of the kayak relative to the water. I'm going to get for the x direction, I'm going to get a 1.5 meters per second times the cosine of phi. And for the y direction, I'm going to have a negative 1.5 meters per second times the sine of phi, negative because it points downward, it points toward the south. If the current's going to carry me north, I need to steer to the south. What I would like to do is travel directly east. If I'm going to travel directly east, I would like my north-south velocity to be 0. And this actually sets me up with an equation that I can solve. So I'm going to take this y column and solve it. So phi is going to be the inverse sine of that. Just like I did with inverse tangents, I'm going to do it with inverse sine. This works out to be 41.8 degrees. This was my first answer back here, 41.8 degrees, and that was south of east. 41.8 degrees, and that is south of east. That answers my first question. How should I orient my kayak? I'm going to go all the way back and look at what the second question is. How long will it take? How long tells me I am solving for t. I'm going to go back here and I can fill in my table. I know this thing equals negative 1 meter per second, so that column would be 0. And this one, if I do 1.5 times the cosine of 41.8 degrees, I get 1.12 meters per second, which means over here 1.12 plus 1.73 is 2.85 meters per second. I am looking for the time. I'm moving at a constant speed. I'm going to use my regular equation 1. X final, X initial, V initial t. T is what I'm looking for. Half a t squared. My acceleration 0. My x initial is 0. So my t is going to be x final over v initial. I get 400 meters. Over 2.85 meters per second. Get about 140 seconds. Or if you like, 2 minutes, 20 seconds. That's it. That's relative velocity.